All right. So we're going to go ahead and we're going to graph each of these 3 lines right here. So this is very similar to what you just did in the Desmos investigation, right? We had 3 pieces. You wrote an equation of the line for each of those pieces, and you first graphed each of them separately. This is one way that we can graph a piecewise function. It is the most basic way. If it works for you, then this is great. If you get more familiar with it, you'll probably come up with shortcuts for yourself and stuff like that, okay? So what we want to do is we want to go ahead and graph this line on this graph, second one on the second graph, third line on the third graph, okay? And then if you're ahead of us, here's what we want you to do. If you're unsure, don't break out your highlighter yet. Just use your pencil and erase if you're wrong. But in graph number 1, we want you to highlight the portion of the graph that's in the domain where x is less than 1, okay? Just on the actual graph, not the whole grid, just the piece of the graph that is in the domain of x is less than 1. In graph number 2, we want you to highlight the portion where 1 is less than or equal to x is less than 4. And in graph number 3, where x is greater than or equal to 4. Does everybody understand that? Okay, so go ahead and start that. All right. I know, be amazed, right? Okay. Is this gadget down here? I'm not magic, okay? All right, so take a look. Make sure your graphs match. Make sure I didn't make a mistake in my counting, okay? Are we comfortable with these graphs? All right, so now let's talk about what it said. It said in the first graph that we want to highlight the portion of the graph where the domain is x is less than 1, okay? So think about where x is equal to 1. Here on the x-axis, a value of 1. That corresponds to a certain point on your line, right? So this point up here that I'm now pointing at has coordinates 1, something, all right? Is that point included according to the way I've written the domain here? No, it's like the end point, but it's not included because I didn't say x could equal 1. I just basically said it goes up to 1, right? So this point is going to be an end point, a little thick. Is that as thin as it'll get? But it will be open. I can't draw it open. I will draw it the other way open, out of practice. Okay, so it'll have an open end point. And then which portion of the graph represents the part of the graph where x is less than 1? Yeah, okay, so, and it's not about being below because it said less than. If you just look at the x-axis, this is 1, and these are all the x's less than 1. And these x's made all these points on the graph, right? So that's how I'm picking that, like, this is the piece of this line that I would want. Okay? The second graph says I want x to be bigger than or equal to 1, but at the same time I only want x's that are less than 4. So basically I want x's trapped between 1 and 4. Is that all right with everybody? Okay. So here's where x is 1. Here's where x is 4. Okay? That makes my endpoints here and here. In the domain restriction on this piece of the graph, is x allowed to exactly equal 1, the way that the restriction is written? Yes. Then this point 1, 3 will be a point that is included in this segment, okay? Because I was allowed to exactly equal 1, so I include that point completely. Is the x value of 4 included in the domain restriction? No. That means I want to come all the way up to that point, everything in between, but I don't actually want to count an x value of 4. So I don't want that 0.4 comma something included, but I want to go right up to it. So I'm going to leave it as open. And so what I want to include from here is all of this, with a closed endpoint here and an open endpoint here. And that captures every point from that segment that has a point where the x value is between 1 and 4, including 1, not including 4, but right up to it. Okay? And then lastly, in this third segment, the domain restriction was where x is greater than or equal to 4. So 1, 2, 3, 4. Here's 4. So here's that point on that graph. Is it included? Okay. In this restriction, yes, x can equal 4. You can have a 0.4 comma something exist on this portion of the graph. So I do want that point. And I want to include all x's that are greater than 4. The x's that are greater than 4 are these numbers on the x-axis, which correspond to these points on the line that was created here. Okay? So in this section, I would want to include everything forever in that direction. Okay? Is this idea all right with everybody? Okay, so now what we're going to do, when you look below that on the page, it has a really funny looking function and it has one graph, but it still has the same 3 branches written down. But it's written in a different notation that means I don't want these things graphed separately. I want them graphed, okay, just like Ariane said, okay, that I want these 3 linear functions, but I only want segments of them, but together they make one picture or one graph or one new function that I'm looking at, okay? So what we're going to do is we're going to put these 3 things that we just highlighted together into one graph, okay? So you guys work on seeing if you think you understand how that plots. I'm going to change the screen so you're not going to see this, unfortunately, anymore, okay, because it's going to erase when I move it up. But I will put together on the bottom and talk about another way we could graph it. So way number 1, you could graph one of these weird looking functions is you could literally do what we did in the investigation in here. You could graph each piece separately, build an understanding of which part of the piece you wanted, and then bring them together on one graph. That's a long process, but it might be useful at the beginning when you're trying to understand how these things really work. Okay? Shorter process, especially with linear functions, is if I understand the notation, right? And do we now understand that this notation means everything I wrote out in words up here? Okay? And you guys know how mathematicians are, right? Do they like writing a lot of words most of the time to mean things? There's like a symbol that means like everything, right? They have symbols for everything. So this is the symbol for please graph this line that is only included in this domain of that function. Please graph this line in this domain and this segment and this domain to create this new graph. Instead, they just write it like this, okay? So one function, 3 pieces, each piece only allowed in a certain portion of the graph, all right? Okay, so we have our 3 pieces. We'll put them together. Yes?
I noticed that in the, for the x coordinate, the 1 has an open dot and a closed dot.
Okay, did you guys hear her question? So she noticed that here the x is not in, the 1 value for x is not included, but in the second piece it is. Okay, and she said, so how would we include that? Well, one of 2 different ways. If this was a graph where those things didn't overlap, then you have this first branch coming up and one's not included. And then at the next branch, you plug one in here maybe, and then it goes like this or something like that. Then it would be included in the piece that it's included in and not included in the piece it's not included in. However, if they overlap each other, okay, so let's say that you go plug and you get the same endpoint that you got right here. Let's say it's 1, 5. This one went right up to 1, 5, but didn't include it. This one also has 1, 5, but it's now closed and included. Is 1, 5 part of your graph then? Yes. So it eventually just looks like part of the graph. So you know how on Desmos when you guys did your graph, it just kind of looked all connected, even though we had the 3 separate pieces. That's because the endpoints overlapped. So even if you left one open but then closed the next one, it eventually became a continuous part of the graph where everything was connected. So if you have endpoints and they're separated, you need to be really careful about what they're like. If they overlap and one's open and one closed, you have that point on your graph. No one really knew that it came from this one instead of that one. Is that okay with everybody? All right, so if we put these on there, okay, so here's how I'm going to do it. I'm going to find this endpoint really quick because I have to graph it right now without having my 3 pictures in front of me because my software takes it away, right? So 1, when I plug into that function, gives me the point 1, 3, right? So I know that 1, 3 is an endpoint and that it's open because 1 wasn't included. And then I am really good at graphing lines. So I understand that a line with a slope of positive 2 went like this, and it had a y-intercept of 1. Okay? Second one here, when I plug 1 into this function, I get 6 over 2, which is 3. So one endpoint for this line is 1, 3, and this is what she was talking about, right? 1 is included in one, but not excluded in the other. But 1, 3 sits right on top of this that was already here. But now it's closed in because it was included in that one. Okay? Then, when I plug 4 into this, I get 3 over 2 as my answer, which is like 1.5. So 4, 1.5. But it's open. And there's that second segment. Okay, but why am I able to do this? I'm really good at graphing lines, right? I totally understand how they work. And I understand exactly how a piecewise function works. If this is too new for you to understand how it works, you go back and graph separate pieces and understand which part. Or on here, you graph the whole thing, erase the part you don't need, graph the whole thing, erase the parts you don't need. There's several ways that you can get it if you understand how to read this notation. Right? And so then finally for this last piece, it's a constant function. Okay, but it's only existing for x greater than or equal to 4. So 4, 1.5, which overlaps this point, and then it just is horizontal over. Okay, so this function, those endpoints ended up overlapping, so they all are closed in and they actually exist on our graph. Okay, because it might have been open, but something else covered it up, and that point is part of the graph. Right? Is this a function? Okay, by definition, function is for every input you have one output or it passes the vertical line test, right? Because every x will only cross it maximum of 1 time, not more than once. And this still passes that rule, okay? So yes, this is a function. Okay. Is it continuous? Yes. That means not separated, essentially. It actually means exactly what it sounds like. Can you draw it without lifting up your pencil, okay, from left to right? You could. So, yes. What is the domain for this function? So what x values are you allowed to plug into this function? Yes. All real numbers. Are you guys okay with that? If you have something less than 1 to plug in, it goes here. If it's something that's equal to 1 and up to 4, it gets plugged into this branch. If it's bigger than 4, it gets plugged in here. Now, our example on Desmos, did it have a domain of all real numbers? No, we came across a number. We did an example we couldn't plug in, right? We could not plug in 6. It didn't work, okay, because we didn't have any graph that went to 6. So the domain was a little more restrictive, okay? Yes? We're going to talk about that in a minute. So, all real numbers, that's a capital bold R when you don't have a bold pen or a typewriter or a computer, okay? That's what that extra little line there means. So we are going to work in this class on interval notation, okay? We're going to get better at it as we go. So interval notation just means tell me from what x value to which x value it's included. So like here it would have a 1 and a 4. Because this piece is only between 1 and 4. But you guys have all real numbers, which means there's no bottom number and no top number, right? For the x's, there's no limit. So when there's no limit, we use infinity. So because there's no bottom limit, we use negative infinity. And because there's no top limit, we use positive infinity. And then we enclose that in symbols that mean something, okay? If you don't reach the number, you use a parentheses. If you reach the number, you use a bracket. So like if I was just writing the domain for this one right here, this can be written like this, 1, 4. From 1 to 4, where 1 is included, but 4 is not. Infinity is an idea, not an exact number. You can never fully reach it. So it would always use a parentheses because I don't know how you'd like plug in infinity. So it doesn't get a bracket. Okay. So another way to write all real numbers is to say from negative infinity to infinity. Okay. All right. Range. What's the range of our function? Yes. Good. So the graph hits 3, but nothing above 3, but everything below 3 because this branch keeps going down here, right? So y is less than or equal to 3. Or, okay, how can we write that in interval notation? Yes. Oh, sorry, Chris. Yeah.
You do parentheses negative infinity to 3 and then bracket.
Are you guys all okay with his notation? So bottom, what's the minimum value? There isn't one. It keeps going down forever. Top, what's the maximum value? 3. So anything below but up to 3. Infinity we can't reach. Do we reach 3 exactly? Yes, with that solid point right there. That's why it got a bracket. Okay? Yes? Parentheses, sorry. These are both parentheses. Infinity will never have like a bracket.
So, no, for range,
Uh-huh.
it has one parenthesis.
One parenthesis and one bracket, yes. Because each one is telling us something different. It's like when you write this with two things, a beginning and an end, that these symbols could be less than or could be less than or equal to, and they're each unique, right? Just because this one has an equal to, does this one have to have it? No. And these are trying to tell us the same thing. So they could be different, they could be the same depending on the situation. Okay? Does everybody have a decent idea of how to graph and put together a piecewise function? Yes? Okay. Good. And we're totally not going to have time for our quiz, so we're going to do it tomorrow. Don't tell Miss Patterson's class. Please. Okay? All right. Then let's look at the top of this page, the part that we didn't do, and that's what I want you guys to work on in your group right now. So it's a problem that exists kind of in a piecewise arena. You can see where these problems would be really real life, because most of the time in real life, a behavior doesn't continue infinitely in the same way. Like if something's growing like a quadratic, it usually doesn't keep growing like a quadratic forever. It'll either turn into something else or level out and be even or something like that. So piecewise functions are really good to describe certain contexts or situations in real life, because most of the time in real life we don't infinitely do one behavior, especially when it's growing or decreasing at some crazy rapid rate. It'll model like that for a while, but then it will change due to something else, usually like population growths and things like that, okay? We can model certain ones with one function, but then they might take a jump, or there might be a plague or something and they decline, and then we have to model them with some other function to that point, okay? So as we learn other functions, you guys will start graphing not just with lines, but there could be like a quadratic part here and then an exponential part here and a linear part here, because those are things that are probably more applicable to situations later on than just having one thing go infinitely forever. But we first have to learn them all, and we're going to learn them that way when we graph them individually, okay? So you guys just work on the top part. I'll walk around and help anybody with any remaining questions.